And so thank you all. And I want to just start by saying Susan and I feel very fortunate to have known Lou earlier in our careers. And Lou makes mathematics fun, and he makes research fun. And his generosity and his encouragement really are a model for all of us. So thank you, Lou. So this is joint work with Lou and Susan Williams, and I'd like to talk about the Penrose polynomial. So first, a word about the four-color theorem, although I think I'm telling people what they know. The four-color theorem asserts that every map in the plane can be colored using only four colors in such a way that any two adjacent regions receive different colors. It was originally proposed in 1852 by Francis Guthrie, who was a former student of De Morgan, and a proof was given in 1879 by Kemp, as everybody knows, and a year later by Peter Guthrie Tate. And both of these proofs turned out to be deficient, but the theorem was finally proved by use of a computer in 76 by Appel and Hawken. So this is so Tate's proof of the four-color theorem was incomplete, but it did establish something very useful. The statement of the four-color theorem is equivalent to this. Anytime you have a bridgeless cubic graph, it will have a plane graph. It will have a proper edge 3 coloring. Now, a cubic graph is one whose every vertex is degree 3, and it's plane if it's embedded in the plane, right? So a bridge is an edge that connects two pieces of the graph. So the bridge is something you remove it and you've disconnected the graph, right? A proper edge 3 coloring is an assignment of colors 1, 2, 3 to the edges, so that at any vertex you see all 3 colors. All right, so that's Tate's version. So we're going to focus on cubic graphs. Every cubic graph has an even number of vertices. This is an old result of Euler. And a perfect matching is just the choice of edges that covers all the vertices once. So any vertex is contained in exactly one edge of the perfect match. So in the following, when we say GM, I'm going to mean a cubic graph with a perfect match M. Okay, and I'm going to draw all the perfect matching edges in red. Okay. All right, so let's talk about N colorings of GM. This is a little odd, so let me be careful with this. An N coloring is going to be an assignment to the non-matching edges. So we see over here a matching edge E, and we've got two colors, I and J. And you see the same pair of colors at the top as you do at the bottom, but they can be switched in order, right? So here's one possibility, I and I on the left side and J on the right side, or I and I on the opposite, on diagonal sides, and J on diagonal sides. So if you can do this everywhere in the cubic graph with matching, then you have an N coloring. One thing to notice is that 3 colorings are really the same thing as proper edge 3 colorings that Tate considered. Why? If I've got 2 colors, I and J, then they appear down at the bottom here, and I've got a third color. So I make that third color the color of the bridge, of the match, sorry. And going the other way around, if I have a 3 coloring, in the sense of Tate, 3 edge coloring, then at any vertex, in particular the one I'm circling here, we'll see all 3 colors. Well, down at the bottom, I see 3 colors, but I can't use this color, so it's got to be these top 2 colors, meaning that I've got 2 colors on top, 2 colors on the bottom, and I've got a third color for the matching edge. You know, so these are the same idea in the case of 3 colorings. So what we now call the Penrose polynomials is interesting. It really is implicitly defined in a paper about abstract tensor systems that Penrose wrote in '69. And the point is that its value at any positive integer is the number of proper edge coloring, 3 edge colorings of G. That's what Penrose wanted. He was hoping to find a proof of the four-color theorem. And of course, this was before the four-color theorem was finally settled. There's a generalization of the Penrose polynomial for ribbon graphs, and this has been developed by Ellis, Monahan, and Moffat. It's different. There's another generalization that was given, the one I'm talking about today, was given by Lou. And it's for graphs that are virtual. equivalently, these are any graphs. They don't have to be plane graphs. If edges cross, as you see in a moment, then we'll make them virtual crossings. In both cases, the polynomial is defined using a skein computation. So here's the story. Last year, Lou gave a virtual talk at University of South Alabama, and he described the polynomial. And what I want to present to you is a non-skein view of this we call Penrose-Kauffman polynomial, P. And this one allows us to interpret the combinatorial significance of the coefficients. That's one of the things it does. It also suggests some topological, possible topological views of the polynomial. So this will be a little strange. Here's a definition of the called the PK, or Penrose-Kauffman polynomial. It's simply a polynomial for GM such that P evaluated at n is the number of n colorings for any n. That's the definition. So of course we have to establish that it exists, but the uniqueness now is immediate because you've got a polynomial that's been specified in an infinite number of places. Right? So this is what we'll take as a definition. All right, so let's talk about, first of all, moving into the realm of link diagrams. Let GM be a cubic graph with perfect matching. Draw G in the plane. It doesn't matter how you draw it. If G is embedded, if G is not embedded, excuse me, if G is not an embedded, then we're going to circle the crossing points of edges. We're going to always assume, of course, that these edges meet transversely. And just for convenience, let's assume no edge actually crosses a matching edge of the cubic graph. So associated to GM is a virtual link diagram, and this is very easy to build. So look over here at this picture. We've got E, that's a matching edge, and I'm simply going to replace it with this crossing. I'm going to think about this over edge here as something that if I turn it counterclockwise, it sweeps out this region that had the matching edge in it. Likewise here, sweeps out the region that had the matching edge in it. Or equivalently, I'll put two dots. This is an old convention, I think goes back to Alexander. Putting two dots here instead of drawing this picture, I'll just draw a projection and put the two dots in to tell us which way the crossing goes. So let's do a real simple example. Here's one down below. It's got a virtual crossing. So I've embedded this cubic graph in the plane, but it does have a crossing. It's got a matching here and here. And so this edge becomes this crossing, and this edge becomes this crossing. And I'll call this D, and this will be our diagram, and G is the cubic graph. Oops, sorry, that way. So working with link diagrams is very convenient and incorporates the choice of perfect matchings, but you don't have to have the perfect matching in front of you. All you need is a link diagram. Every link diagram will give you one of these cubic graphs in this way, and vice versa. And also, it motivates some topological questions, as you'll see, about the Penrose polynomial. Okay. All right. So this is an important point for what I'm going to do. A state S is the virtual link that we get by smoothing subsets of crossings of the diagram. I'm only going to be working with the diagram now. So let's work with the diagram and let's pick some crossings and let's smooth them. By smoothing, I mean a smoothing. Whereas I open up a channel so that these dots can come together, you see. And if I don't do that, I'll call it a cross. If I do smooth it, I'm going to call it a kiss. So we have kisses and crosses, and this is really all we need. So here comes a very important definition. A state S is colorable if each kiss or cross that you see involves two different components of that state. Or said another way, there's no component kisses itself or crosses itself. That sounds awful, but that's one way to say it. Okay, and once we have a colorable state, it makes sense to talk about coloring. So if I have a colorable state S, and n coloring is an assignment of colors 1 through n to the components of that state, such that any two components that kiss or cross will receive different colors. Okay. And examples below. So at the very bottom of this example, you see the diagram, And I've only got two crossings, so there's only going to be a total of four possible states here. The diagram itself, the one where everybody is smoothed up at the top, and these two in the middle where only one thing is smooth. I've arranged these so that each level you see the number of crossings. At the at the bottom, it's all of them, two, and then one, and then none. But there's only one diagram here, which actually is only one state here, which is actually colorable, and that's the one I've circled with here in green. As you can see, the problem with the bottom, for example, is that you have a component crossing itself. Here you have a component kissing itself, but this one's fine. It's got two components, and for any state. Well, let me go back a moment here. We've got two components, and notice that each one crosses. If I wanted, I could color these so that one of them is colored with n colors, and the other one would be colored with what, n-1 colors, and this would be an n coloring of this state. For any state of a diagram, we can count the number of n colorings with a famous chromatic polynomial of a graph that we construct GS. So what's the idea? You give me a state, and I know I've got these components. I'm going to take vertices that correspond to the components. And a single edge, only one edge between components if they kiss or if they cross. And if I build this little model, then all I have to do is compute the chromatic polynomial of that little graph, and that will tell me how many n colorings or q coloring or whatever n colorings I have of that state. All I have to do is plug n into the chromatic polynomial, because that's what the chromatic polynomial does. It counts the number of colorings for just plugging it in. These are, of course, vertex colorings in the chromatic polynomial. That's what we're looking at, because each vertex corresponds to a component of the state. Okay, here's the main theorem. Let GM be a cubic graph with perfect matching. Let D be the diagram associated to it, the link diagram associated to it. The PK polynomial is simply the sum of the chromatic polynomials of the colorable states. So before I say anything more, what you don't have any negative coefficients. We're just adding chromatic polynomials here, right? The proof of this is remarkably easy. Here's a picture just to give you the idea of the way it goes. At the top, I've got the cubic graph. At the bottom, I've got the colorable state. Suppose I were to color the cubic graph, I and J. There's an I here. You can see I didn't write it in. There's an I here. So there's an I here and there's an I here. And what we're going to do is we're going to color this crossing by that color. Likewise, there's a J here and a J here. I'm going to color by that crossing. And so if you look at this, it doesn't take very long to see that if you've got an N coloring above, it will give you an N coloring below. Now, there could be more colorable states, but what you see is that if you color the top, if you color the graph, you'll find the state, and there'll only be one that can be N colored with that color, because up above you really got instructions as which state you're going to be using. For example, if this color and this color were the same, then I'd be talking about a smoothing state for this crossing. So, and likewise down below, if I have a coloring down below, I can lift it up to a coloring of the cubic graph. And this is not hard to check, but this is the only thing there is in the proof. Okay, let's talk a little bit about the original skein approach. This is done by a skein computation tree using Penrose relation. This is the Penrose relation. The leaves of the skein tree are the states of the diagram that we've been talking about. So if there are n edges in the perfect matching, there's going to be 2 to the n leaves at the bottom of the computation tree. Each one would get a value of plus or minus q to the number of components of that state. The algebraic sign is interesting. It's the sign of a product of weights that you get along the edges of the computation tree. But there's also an adjustment that will depend upon the virtual crossings that you had. If you look closely at that computation, you'll see that it really is taking into account a a homology Z2 intersection number of curves on a surface. So there's a lot going on there, and generally many of these terms will cancel. Okay. If you look at a graph that you've put in the plane, like this one here, a little segment of it, and you twist it, as we do at the bottom, getting a virtual crossing, you'll see that what's happened is that the basically these two contributions to the polynomial have been swapped. This one now is going across, and this one is now going straight down. And so you can see why there would be some adjustment that would be needed in the leaves to make sure that you get something that only depends on the graph. And so the approach that we're using here will avoid this. All right, I want to characterize these colorable states because they have a very interesting and simple interpretation. Consider the set S of all states of some diagram that we've got associated to GM. And let's define a distance metric between states. So it's equal to the number of places where the two states differ. All I mean is that you look at the crossing sites of your diagram and you see, how many places you made a decision to smooth for one and say cross the other. So wherever the decision was different, you count these up, and this is the distance between the two states, S and S prime. Also, let C be a function which just tells you the number of components of the state you're looking at. So I'll call that C, capital C. And here's a surprising proposition. A state is colorable if and only if this state is a strict local maximum point of this coloring count. The proof of this is also very pleasant. If S is colorable, then at every crossing site, two components cross or kiss. If you change the site, cross to a kiss or kiss to a cross, you've got to reduce the number of components of the state. All right, so you were at a strict local maximum. Conversely, if you're not colorable, then at some crossing site, two arcs of some component, somewhere there will be a site where two arcs of a component cross or kiss. And if you change the site, you can't reduce you can't reduce one component to no components. So you're not going to reduce the number of components of the state. All right. So let me say something here about alternating link diagrams, because your first thought might be, well, these diagrams are nice, but this is not a topological invariant, right? Yes and no. Let me explain a little bit. If you smooth every crossing of a classical, that means no virtual crossings, alternating link diagram, or more generally, if you know what this is, a classical adequate diagram, then this produces a colorable state in an alternating case. And it has the maximum number of components among all states of the diagram. I won't go into the proof of this, but let me say that at least the way that we saw it is by characterizing the components as left-right walks in a plane graph, and looking at the Z2 the nullity of a Z2 Laplacian matrix. I won't go into the details of it. They're not hard, but it's take us a little far afield. So let me just make the statement here. The PK polynomial is an invariant under Fleiping. That's also not too hard to see, and let me not go into it. But as a result of this, of course, we get a proposition, which is that the PK polynomial of a reduced alternating link diagram is actually a topological invariant of the link. So yes, there is some topology here associated with this interpretation of the polynomial. So it's time to do an example. Let's look at a left-hand 2n torus link. All right. So if you consider the 2n torus link diagram, which is right here, it's not, and over to the left actually is the graph that you get that you get it from. So I've got two circles here, and I've got a bunch of edges here. There are n edges, matching edges. It turns out that there's only one colorable state. This is not hard to see. That colorable state is here. We've smoothed everybody, both the totally smooth state S sub m. I use sub m because m is the set of matching edges, and they're in corresponds with the number of crossings. So basically, I've smoothed everybody in M. So now, if you look at this, we've got n circles. There's a big one on the outside, and there are ones in the middle, but they all connect each other like a circle. And so the graph associated to this is to the right. It's a cycle graph, and the characteristic polynomial of that is, I'm sorry, the chromatic polynomial of that is well known, and it's up here. And since that's the only colorable state, this is the Penrose Kaufman polynomial of GM. There are 2 to the n leaves in the skein tree computation, but most of them cancel, and really there's only one state that's needed here, and that's so again we're trying to avoid using all the leaves of computation scheme. If n is even, oh, I didn't. Let's see. Did I say? Yeah. I'm sorry. I think I didn't say that n had to be odd here. I'm sorry about that. N is odd in this picture. But if n is even, then there is one more colorable state. So I lied a little bit. That colorable state would be the link itself. In that case, you would have 2 circles that kiss. And I'm sorry, that cross. And so in that case, this would be another contribution to the polynomial. And when we add q times q minus 1 to this polynomial, we get this at the bottom. So this is what you get for n even. Okay, let's talk about the right-hand 2n torus link. Very different. The colorable states are those with an even number of crossings. It's not too hard to see. And each of these, each consists of 2 kissing or crossing components. They're exactly 2 to the n minus 1 colorable states. Why? Because you're summing up all the possibilities. N choose k where k is even, and that's going to be 2n divided by 2. So 2n minus 1 colorable states, and each one is 2 circles that are again are crossing or kissing. So you get q times q minus 1 to the n minus 1. And oops, let's see. There you go. For an alternating classical link, by the way, it turns out that this leading coefficient that you're seeing is always a power of 2. And that's not terribly hard to see, but I'm not going to go into the details of that. Well, the degree, if you checkerboard color the regions that have dots in them, so that the regions with the dots are unshaded, and the regions that don't have dots are shaded, then the degree of P is actually the number of unshaded regions, because it's the number of circles that you get in the totally smooth case. And if you the number of shaded regions is the degree of the PK polynomial for the mirror image. So if D is reduced, then P can actually distinguish the alternating link from an alternating link from its mirror image if they're different. Here's down below. This is a familiar thing for in topology for Jones polynomial and so on. Let's do a more serious example. Here's the complete bipartite graph K33. Associated diagram has only 2 colorable states. So again, I've drawn all the states. At the bottom, you see all the crossings. At the top, you see no classical crossings, and each level has different number of crossings, right? And it turns out that they're only this one at the top and this one at the bottom are the only ones that are colorable. For example, if I look at this one over here, I see a component that is crossing itself and also kissing itself. And up here, let's see, up here we have things that are, this is a self-crossing and so on. But this one at the top is 1, 2, 3 circles. You don't worry about that virtual crossing. Just, this is a circle. Just ignore it. And got 3 circles and they're connected in a cycle. So we get a complete graph on 3 vertices for the graph whose chromatic polynomial gives us a contribution of this state to the polynomial. q times q minus 1 times q minus 2. The bottom, there's two circles. I get q times q minus 1. And the pk polynomial is right here. It's q3 minus 2q squared plus q. I now want to switch gears a little bit. I want to show you what knowing that the polynomial is a sum of chromatic polynomials will do in terms of helping you find out information about the coefficients of the polynomial. So assume GM is a cubic graph with perfect matching. Let CM be the number of M colorings of GM using exactly M colors. So the number of N colorings of GM is going to be a summation of these things where you multiply each one by N, choose M. Why? If I've got N colors, I decide how many I want to use. And I've got to make my choice of colors, M from the N set of N. And then I count the number of ways I can color with exactly M colors. And I do this for each M, and there's no overlap here. And so this is the value of P evaluated at N. So I just replace N by Q. And what do I mean by Q choose M? Well, this is Q times Q minus 1 up to Q minus M plus 1 divided by M factorial. This numerator is sometimes denoted Q sub M. This is the folding factorial QM divided by M factorial. And these folding factorials form a polynomial basis, just like the powers of Q. So now we get two formulations of the pk polynomial. One is a summation of these folding factorials times Cm divided by M factorial, just as we had a moment ago. But now think about what Cm divided by M factorial really means. It's the number of ways to color with exactly M colors, but then you get to rename the colors if you divide by M factorial. So Cm divided by M factorial, we're going to denote by Em. And it's going to be the number of ways to color with M colors using all the colors, but up to renaming the colors, right? So it's just some terminology. So here's a immediate proposition that we get from all of this. The chromatic polynomials all are monic, and they have highest coefficient 1. So you just have to look, if you want to know the degree of P, it's the largest number N, such that G can be N colored using all N colors. And the leading coefficient is En. It's the number of ways to color up to renaming colors. Okay, so this is immediate. So the leading coefficient, whether you're writing your polynomial in terms of powers of Q or powers of following factorials, will be the same. Now let SNK be the Stirling symbol of the first kind. So its sign is -1 to the n minus k, and its combinatorial meaning is very simple. If you think about the number of ways, say, to seat n guests at k non-empty circular tables, that's what SNK is. In particular, you know, if you've got more tables than you do people, if k is bigger than n, then this number is 0. And it's very well known that if you want to write the following factorial Qn in terms of the standard basis for polynomials q to the k, then you do it as a summation like this. So we get a theorem. The kth coefficient of the pk polynomial, written as a polynomial in powers of q, of course, is given as a summation of the Stirling symbols SMK times Cm over M factorial, or times Em if you wish. It doesn't matter. This is the formula for AK. Let's see how the proof goes. It's pretty nice. So first of all, I start by writing pk the way we did a moment ago, but now I take this formula for Qn and I simply plug that in. I change my order of summation. This is a finite summation. And rearrange things. Here's q to the k outside, and here's the term that I claim is AK. This is the coefficient of q to the k. If in particular, if you want to look at A1, then you'll need the Stirling symbols SM1. And these are -1 to the m minus 1 times m minus 1 factorial. That's easy. And if you plug that in, this is a formula that we'll get for A1. Now think about this for a moment. This is saying we look at all the ways to color with m colors using all of them. And we take in we'll take an alternating sum. It's like an alternating harmonic series sum. And this is A1. I'm gonna have something more to say about A1 in a minute. But notice that it has always shown up in these calculations so far, that it's always been non-zero. Okay, Stirling symbol of the second kind, denoted by capital SNK. This counts the number of ways to partition n elements into k non-empty sets. And these are used for writing Qn in terms of the following factorials. They're sort of inverses in some sense of each other. Qn is written this way in terms of the following factorials. So in the same way that we got this formula before for AK, now we get a formula for EK. These are the coefficients writing your polynomial in terms of following factorials. EK is equal to the summation of Stirling symbols times the coefficients of the PK polynomial with in terms of powers of Q. Good example is the Baromean rings. This is always a great source of examples in knot theory. So the Baromean rings, there are 64 states. The way I've drawn it, I've picked the matching. And by the way, I didn't say it, and I want to make sure I really do say it. This Penrose Kaplan polynomial depends on the perfect matching. I could have chosen a different perfect matching here, and you will get most likely a different polynomial. But of course, the evaluation at 3 will be the same. But when you use the link diagram, you sort of forget that you know this thing came from something with perfect matching. But anyway, this is the perfect matching that we'll consider. So look at the Baromean rings with this matching. Here's the link diagram over here. It turns out that there are 64 states, of course, and it turns out only 2 of them are actually colorable: the link itself and the completely smooth state. So the link itself has got 3 components, and they all cross. And the smooth state has 4, and they all kiss. So we immediately get the chromatic polynomial for K3 plus the chromatic polynomial of K4. And here it is written out. And so in particular, since the coefficient of the following factorial Q4 is 1, and following factorial of Q3 is as coefficient 1, we see there's only one way to 4-color this graph using all colors up to renaming. And similarly, there's only one way to 3-color. But let's mess it up. So here, I've changed this crossing. That's the dot used to be here and here, and I've changed it to there and there. And I've removed it here, and I've put in a virtual crossing. And it turns out that this example has 3 colorable states. I won't draw them out, but it turns out that suddenly this linear term is missing. It's Q3 minus Q2. And I want to conclude with a couple of conjectures. Here they are. Let GM be a cubic plane graph with perfect matching. The sequence of coefficients of P alternate in sign. Everyone is an alternating polynomial, has no interior zeros, by which I mean you're not going to see some coefficient of 0 in the middle. So it's what you'd mean by alternating polynomial, alternating sign polynomial. And the coefficients are log convex. Also, the second conjecture is that the linear term of P is non-zero. This is for plane graphs. All right. And a couple of remarks here. Statement 1 was actually proven by Jin Ha in 2012 for chromatic polynomials. I mean, it was already known that chromatic polynomials have a sign alternation. It's very easy to show, but the rest of it, the log convexity was not clear. And this is a pretty amazing paper. It really turned out to be the fact that that the chromatic polynomial is what's called a characteristic polynomial of a matroid that is representable over a field of characteristic 0. And if one can show that for the PK polynomial, then conjecture 1 would follow. Ian Moffat tells me that for plane graphs, the version of the general Penrose polynomial that he and Ellis Monahan provided actually does satisfy such a matroid. So it would be natural to look for it in this example, and for this generalization, I suspect it's there. And as far as the linear term goes, as we just saw a moment ago, it's false unless you assume that G is a plane graph, and because of the Bromian ring example that we modified. Okay. So that brings me to the most important slide of the presentation, and that's thank you for listening, and happy birthday, Lou. Thank you.
Thank you, Professor Silva. Now I shall stop the recording, and if